Hello everyone, we are continuing on with trigonometry review. If you haven't done the reading, please do so. It'll be Kinetic Chapters 1, 2, and 3, OpenStax Chapters 2 and 3 if you're in Physics 111, and OpenStax Chapters 2, 3, and 4 if you're in Physics 121. Alright, so we're just reviewing trigonometry, okay? So the basis, the tools that we need to use for just trigonometry is going to be sine, cosine, and tangent, okay? So sine of theta is opposite over hypotenuse. Cosine of theta is adjacent over hypotenuse. Tangent of theta is opposite over adjacent. Pythagorean's theorem is c squared equals a squared plus b squared, okay? So that is the basics. Besides vector addition and what we just did, you're going to need to be able to use these tools, really important. And you need to be so efficient at it that your brain is going to almost come up with the answer before you even can really think of how you got that, right? So we need to get you really, really efficient at using trigonometry because we're going to be doing a lot of decomposing of vectors into their unit vectors, okay? So let's try doing some practice stuff. So here we have a major vector C that has been decomposed, right? We did this all last time. You have a vector that's pointing up and to the right. So what that is it's a CX vector. It's a right vector and then an up vector. So it's a positive CX vector, a positive CY vector, okay? And this angle right here, so I'm going to mark this up. So I'm going to go to comments. And now I have my tools. I'm going to give myself some room. So I'm going to then use this to mark the little pencil to mark up the document, okay? So what they're saying is this is theta here, okay? So how do we get theta? How do we get, if we're given the length of this major vector as 4 meters per second, suppose it's a velocity vector, okay? So if we're given that, and we're given this angle theta, or suppose we're not given the angle theta, I don't know. But let's say we are given the angle theta for right now. How do we get the CX vector, okay? So you have this vector pointed up and to the right. Well, then you say, okay, I started here to the right and then up, and you've made your triangle, and you decomposed this vector into its unit vectors, CX and CY. And let's say you've measured this angle theta. How do you get the length of CX given theta and the major vector? Well, you have to remember sine of theta is equal to actually, this will be, you have sine of theta is equal to opposite over adjacent, right? And cosine of theta is equal to, opposite over adjacent. I am so sorry. Opposite over hypotenuse. Cosine of theta is equal to adjacent over hypotenuse, okay? So here, the CX vector, is this adjacent or opposite the angle theta? Okay, we know this is the hypotenuse. That's pretty easy to recognize. But how do you recognize the opposite and the adjacent side? Opposite of angle theta and adjacent to the angle theta. Well, the opposite angle goes, if you draw an arrow directly out from here towards the angle theta, this is now going to point to the opposite. So that means the opposite side is actually going to be CY, and the hypotenuse is C. And if that's the opposite side, well, CX has to be the adjacent side. So in this case, it's going to be CX over hypotenuse, and C is equal to the hypotenuse, right? So now we have a method to do some algebraic manipulation. So if we want to find CX, cosine of theta, and actually I'll do that over here. cosine of theta is equal to cx over c. Okay? So if we want to find what cx is equal to, we need to multiply both sides by c. And if we do that, you get c cosine of theta is equal to cx. Okay? So that means you could define this component vector here, cx, in terms of theta and c as c cosine of theta. All right? And you're going to do the same thing for the cy vector. If you want to get the answer, if you want to get what this vector is in terms of the hypotenuse and theta, well, sine of theta is going to be equal to cy over c. And so this, then, multiply both sides by c, and you get c sine of theta is equal to cy. So now you have what cy is equal in terms of c and theta. It's going to be c sine of theta. All right? If you didn't know what theta was and you needed to find it, well, you'd have to have at least two of these. You'd have to have cx and c. In that case, you'd get theta by using sine, the inverse sine of cx over cy, cx over c. Oh boy. Let's do that again. If you need to find theta in terms of cx and c, well, you take the inverse cosine of both sides, and you get cosine -1 of cx over c. Well, if you have cy and c, then you would do the inverse sine of cy over c. But most likely, if you're in this situation and you have cx and cy, you're not going to have c and theta, so you're going to have to find that. Well, to get theta, you just do the tangent of inverse tangent of cy over cx, right? Because in terms of this case, tangent of theta is going to be equal to, let me close this, is equal to cy over cx, or tangent of theta is equal to opposite over adjacent, which in this case, cy over cx. Anyways, so you take the inverse of both sides and you get inverse tangent of both sides and you get this, and so that's how you get the angle theta. In order to get the length of this, you would do c is equal to the square root of cx squared plus cy squared. So usually what happens is you're given c and theta, and then you have to find cx and cy. Well, this is how I just showed you how to do that. And but the other case most likely is that you're given cx and cy and you have to get theta and c. Well, you would do it here by doing this. Okay. So again, this is just a review, and this is kind of brushing up and shaking off the cobwebs from everything that you learned in algebra, trigonometry. All right. So let's do some just basic vector analysis, and then we're going to add in our trigonometry here. So we're going to kind of review a little bit of what we did before, but now before with the addition of vectors and also decomposing a vector into its unit vectors. So let's do this. I want you to decompose this vector right here. This vector is pointing down and to the right from the origin, and here's the units. The positive y direction is going to be at above, so this is the coordinate system. Negative x is to the left, negative y is down, so this would be -4, -3, -2, -1, And this is going to be -1, -2, -3, -4 in the x direction. So this is the y direction negative. So I want you to decompose this vector in terms of the x direction and y direction. Okay? So into its components. All right? So what answer will you choose here? Pause the video and try this out. So how you do this is you just take a look. So what we're going to do is, what is its x direction component? Well, this vector is pointing to the right, and it's also pointing down. Okay? And so if it's pointed to the right, it's going to be pointed in the x direction. And I just try to find the length of this. So what I did is I created a right triangle, and it's the addition of the two vectors. And again, that would be the hypotenuse. Here's the 90-degree angle right here. And so it looks like that rightward vector is pointing to the right by +3 units. Right? Correct? And it looks like the y direction is pointing down by -4 units. So the x direction component is that, and the y direction component is -4. Well, we want the answers x, y. So we're going to be looking for an answer that is going to be +3 units, or a rightward vector, and then 4 units down. So that looks a lot like B. Hey, cool. Cool. And so that's how to decompose a vector that's in actually 2 dimensions, starting from the origin. It's easier if it starts from the origin, into its unit vectors. Okay? Well, now we're given the same problem, and you need to find what theta is. Okay? Well, there's a lot of ways to do this, but let's try to use the easiest way, the most straightforward way. So go ahead and try to figure out right now, take an attempt to figure out what theta is, and remember your trig functions: sine, cosine, tangent. SOHCAHTOA is another analogy to that. Okay? So go ahead and try that out. All right. Well, this is the same problem as the last problem. So again, this vector this vector that's pointing down and to the right is actually a +3 vector, and it's a -4 vector. Okay. So, and you know what? I'm going to give this. You know what? I'm going to give this guy a name. I'm going to name him I'm going to name this the C vector, and this will be CX, and this will be CY. Okay, so this is the C vector, and this +3 units, so it's CX and it's CY. So let's find out what theta is. Okay, well, tangent of theta is going to be equal to opposite over adjacent. All right, and we're in opposite of theta and adjacent to theta. Okay, well, the side that is opposite of theta, in this case, I'm going to do here and draw an arrow that points towards theta, which then eventually points towards the opposite. So in this case, it's going to be CY over CX. So tangent of theta is equal to CY over CX. So that means theta is going to be equal to the inverse tangent of CY over CX, which is going to be the inverse tangent of -4 over 3. So in order to get what this is, -4 over 3, we have to go ahead and use our little calculator. So I have that up here. So I'm going to put in 4 and make it negative, and then I'm going to divide it by 3. Okay, so it's going to be -1.33. So, and then I'm going to do the inverse tangent of negative 1.33, which is going to be negative 53 degrees. So what this is saying is that theta is going to be 53 degrees, right? So that's 53 degrees. While we're here, typically once you get this, you also have to get the length of that. If you're given the component vectors, okay, cx and cy, usually you have to get theta and then also the length of c. So let's get the length of c. Well, c is going to be equal to, so c is equal to c squared. C squared is equal to a squared plus b squared. That's Pythagorean's theorem. So in this case, it's going to be cx squared plus cy squared, which is going to be equal to the square root of 3 squared plus a negative 4 squared. And so c is going to be 16, the square root of 16 plus 9. Let's find that. So 16 plus 9 equals 25. So the square root of that is going to be 5. And I probably should have recognized that that's a 3, 4, 5 right triangle. Yes, you are smarter than me. I like to be sure. Sometimes I doubt things. So anyways, this is the basics of what we're going to be doing in this class. This is the fundamental parts of motion, which is we're going to have to, since it's vectors, motion is vectors and force is vectors and momentum is vectors, we're going to be needing these tools to actually solve problems. So we really need to know our trig functions and our addition of vectors. Okay, so we need to really be very intimate with trigonometry and vector addition. Let's try another one. So suppose you are given the vector h and you're given this angle 30 degrees. What is the vector y in terms of h and 30 degrees? Will it be h cosine of 30 degrees? Will it be h sine of 30 degrees? Or will it be h tangent of 30 degrees? Go ahead and try it out, and let's see what you get. Okay? Pause the video now. All right, we're back. Well, let's go ahead and do this. I have 30 degrees, and if that's the angle here, and this is the hypotenuse, then the opposite side is going to be over here, which is probably going to be the x, right? Because that's horizontal, okay? Well, y is right over here, so the opposite side is going to be x. This looks like it is. This y side is adjacent to 30 degrees. Well, when I hear adjacent, well, I'm going to list out my functions right here. Sine is going to be equal to, sine of theta is going to be equal to, in this case, x over h. Cosine of theta is going to be equal to y over h, adjacent over hypotenuse. And in this case, tangent of theta is going to be equal to x, opposite over adjacent. Well, we want y, so we're going to have to use this guy, right? We're going to have to use the adjacent one. Well, multiply both sides by h, and you get h cosine of theta, and that is y, right there. Which looks like this one. If theta is 30 degrees, then h cosine theta is y. How'd you do? Well, let's try this out for the x direction one. Okay, so this will be y, and this will be x. So what would x be in terms of h and 30 degrees? Go ahead and pause the video now and try it out. See what you get. Again, I'm going to just list this out. Sine of theta is going to be equal to opposite over hypotenuse. In this case, opposite is x over h. Cosine of theta is going to be equal to adjacent over hypotenuse. And tangent of theta is equal to opposite over adjacent. opposite 30 degrees over adjacent? Well, a pattern is emerging, right? So to get x, you multiply both sides by h, h sine of 30 degrees, and that is x. So this is the answer. So a pattern is emerging. Okay, look. If you are given hypotenuse in 30 degrees, the side that is adjacent to it is going to be cosine. So when you have to do problems where you're given the hypotenuse and you're given the angle theta, and you need to get the adjacent one, you think hypotenuse cosine of theta. Okay, if you need to get the adjacent side, and you're given the hypotenuse and the angle theta, you go hypotenuse cosine of 30 degrees. Just make that association, right? And you're chunking information. You're doing this, you're just making an association that this is a part of this. So when you have to solve for an adjacent side, I want you to think this, okay? When you need to find the opposite side, you should be thinking h sine of 30 degrees. So if you're given hypotenuse in 30 degrees, you should be thinking h sine of 30 degrees. And if you're given both sides, y and x, and you need to get theta, you should be thinking in terms of tangent, which means, in fact, you should be thinking inverse tangent is going to be equal to opposite over adjacent, okay? So you need to be thinking in terms of those, okay? So I'm trying to get you to chunk your knowledge now, okay? Let's try another one. Suppose you have a hypotenuse that is 4 units. So it's a length of 4, okay? And you have 30 degrees. What I want you to do is I want you to get the length of the x component vector. So I'm going to call this C. I want you to get the x component vector length and direction, and the y component vector length and direction. So go ahead and try that now. Again, you're given a C vector pointing up and to the left, and this is 30 degrees. You need to get the x component, so you need to decompose this into its x component and y component in this format. Try it now. Okay, we're back. Well, let's try it out. So this vector is pointing up and to the left. So from the origin, we're going to add an up vector, which is going to be cy, and an x direction vector, which is pointing to the left, and then it's going to be cx, and it'll be pointing to the left. Okay, and this is pointed up. All right. Well, cy is adjacent to the angle 30 degrees, so that's got to be c, the hypotenuse, cosine of theta, which is going to be the hypotenuse, which is 4 cosine of 30 degrees. Okay. The cx guy is it's to the left, and it's going to be the c vector sine, and that's the opposite. So we should be thinking hypotenuse sine of theta, which is then going to be -4 sine of 30 degrees. -4 because this guy is pointing to the left. Okay? All right. Well, let's find out what cx and cy are. Let's use our little calculator that comes on the computer. So I'm going to go 4 negative. So I'm going to do the cx part first, and then I'm going to multiply that by 30 degrees and sine of 30 degrees, and that is -2. So this is pointing to the left by 2 units, okay, and that is cx. The y direction one is going to be +4, And I'm going to be multiplying that by 30 degrees, and I'm going to be doing the cosine, which is 8.66. And that is going to be 3.46. So this is going to be pointing up by 3.46, and that'll be cy. Well, if we want in the format of cx comma cy, what we're going to be looking for is -2 comma 3.46. So -2, which is -2, 3.46 will be this. So it looks like B is going to be the answer. How'd you do? Well, this brings us to a lecture tutorial. Okay? So Mark wrote, this is an amazing lecture tutorial, and it's actually two. I took a picture of two lecture tutorials. Vector Addition 1. So this is the Vector Addition 1 tutorial. This is Vector Addition 2. Okay, and this is a really great way to emphasize what we just did. This is one of the best teaching tools I've ever used. Okay, so let's break it down. Let's do the first pane of Vector Addition 1, which is this. Actually, this is the second pane of Vector Addition 1. Here we go. You have an A vector that is pointing to the left, and so that will be. And so in this thing, we're going to then, you're not to assume that this is a positive A and this is so we're going to be assuming that any vectors pointing to the right are positive X, any vectors pointing up are positive Y, any vectors pointing to the left are negative X, any vectors pointing down are negative Y. Okay, so this guy right here is got a vector A pointing to the left, and it's got a B vector pointing down and to the right. And so you're going to make an equation with this, okay? So the A vector is going to be pointing to the left, and it's only got components in the A direction. So I'm going to make this first part of this equation the A vector and B vector. So we're going to do the sum of vectors here. So this first vector here is pointing in the negative X direction, and all of it, its full magnitude is pointing in the negative X direction. However, it has none of its components pointing in the Y direction. Okay, so that's this guy right here. This B vector, okay, is pointing to the right at an angle 20 degrees below the horizontal, which means it's got a BX component pointing to the right, and it's got a BY component pointing down. Well, if this is 20 degrees right here, and you have to use the angles Mark gives you, okay, Professor Mark gives you, so here we go. You got B that's pointing to the down and to the right. This BX vector, is that going to be adjacent or opposite 20 degrees? Well, that is going to be adjacent to the 20 degrees, so it's going to be B cosine of 20 degrees. The BY vector is opposite that angle of 20 degrees, so it's going to be pointing down sine of 20 degrees. Okay? So that means the X direction component is going to be B cosine of 20 degrees, and it's pointing to the right, and the Y direction component is pointing down by sine of 20 degrees. Okay? All right, let's try, so that's how to do Vector Addition 1, and they're all variants of this, but this is the basics, okay? I'm actually going to grab this. I'm going to grab this thing right here and move it. Rather than move it, what I'll do is I'll just rewrite this. Try to write it horizontally here. So this is going to be negative by, and this will be negative b sine of 20 degrees. The reason why I wanted to rewrite that y direction one is I'm going to need room in here to actually draw vectors. Okay, here we go. So now, so in vector addition 1, you're given the vectors, and then you have to create the equation. Okay. In vector addition 2, you're given the equation, and you have to create the vectors, and that's what I love. This is here you're given. This is hypothetical deductive reasoning. You have to. You already know the rules. You have to create the equation for the rules, right? So this is the conclusion. Here, you're given the conclusion, and you have to create the suppositions, right? So this is inductive reasoning, all right? So you're supposed to, here's the equation that you're given, and you have to go ahead and write those vectors, okay? Well, let's see you try it. Pause the video, and let's see you try this, okay? Well, we're back. Well, here we go. You have the negative a vector right here, right? And if you notice, it's got the format just like we had over here. A vector goes first, B vector, and then C vector, okay? Actually, I'm going to rewrite this so it's a little bit more organized. The A vector goes first, then the B vector, and then the C vector, B cosine of 50 degrees, and then the C vector. Well, here in the y direction, it has no A vector. It does have a B vector, and it's going to be the sine of 50 degrees. And it has a C vector in the y direction, but not in the x direction. So it goes A, then B, and then C. In fact, I'm going to color those. A, then B, and then C. So I'm going to color A red. I'm going to color B blue. And then I'm going to color C green. Okay. Well, the A vector is going to be pointing, it looks like if you look at the x direction and the y direction together, let's just look at the A vector. Don't look at B or C. The A vector is going to be pointing to the left, right? It's got a negative x component, and it has no y component. So the A vector, I'm going to grab a vector here. It looks like the A vector is just going to be pointing to the left. And it's going to be red. So the A vector is pointing to the left. Okay. All right. Let's do the B vector. The B vector, if you look at this, forget about the cosine for a second. The B vector has a negative B component and a negative b component in the x direction and a positive b component in the y direction. So that looks like it's going to be pointing to the left and then up. So we need to draw a left up vector. Okay, whoops. So I'm going to draw a left up vector and up to the left vector. I'm going to make it long to distinguish it from the A vector. I'm going to make the A vector smaller. Okay, so the B vector is pointing up and to the left because it's got a negative b in the x direction and a positive b in the y direction. All right. Well, let's find out the angle theta. Okay. Well, it says the negative b component, the x direction component, is cosine of 50 degrees. and the y direction component is sine of 50 degrees. So what is that saying? Well, it's saying basically it's got a y component that is going to be positive b sine of 50 degrees, right? And that's the y component, right? And the x direction component is going to have, and I'm just drawing the component vectors for this, okay, the x direction component is going to be negative b cosine of 50 degrees. All right? So what is that telling me? Well, that tells me that the x direction component is adjacent to the angle theta, and the y direction component is opposite the angle theta. So what is that saying? Well, that is telling me that this angle right here, from here to here, is going to be 50 degrees. Okay? By the way, this is the b vector. The a vector is going to be red, and this is a vector. Actually, the a vector is going to be red, and that's that guy. The c vector, it looks like the c vector has no components in the x direction, and it has a positive y component in the y direction. So the c vector is going to be pointed straight up. That c vector is going to be pointed straight up. And so this is the c vector. All right? And so that's basically how you do that. I'm sure there's quicker ways to do it, but I kind of like to, if I have a complicated vector like the b vector, I like to break it up into I like to decompose it into its unit vectors and then draw those. Okay? So that's basically how to do this tutorial. So I've been talking about unit vectors this entire time, and I haven't really elaborated on what I mean by unit vectors. Okay? So unit vectors are what is used often in higher level courses, but we got to touch on it here because if you're taking engineering courses, you have to do. So this is for Physics 121 students mainly. So if you're going to go on to engineering and do physics, you're going to do torque. So you're going to do statics and dynamics, and a lot of it is done in unit vector notation, okay? And unit vector notation is I hat, j hat, and k hat stuff, okay? And so unit vectors have magnitudes in units, okay, relative to whatever units you're using, so meters per second or newtons or meters per second squared or meters, things like that, right? And they point along the coordinate axis, all right? So you're using these I hat, j hat, and k hat to specify x direction, y direction, and z direction, okay? I is associated with x, j hat is associated with the direction y, and k hat is associated with the direction z, okay? So in 3 dimensions, it would look something like this. In the x direction, it would be 5 meters per second I hat, right? going to mark this up. So you would say, in this case, this if this is a velocity vector, okay, it would be 5 meters per second I hat, and they would be a positive 5 meters per second I hat, which means it's pointing to the right. In the j hat direction, if it was pointed up, it would be like, let's say 6, or actually let's say 7. It would be pointed 7. Actually, does it? Actually, looks like it's smaller. It'd be positive 4 meters per second j hat. Okay, so they would write it like that. Z hat, they would write it out, right? For example, in and out, the z direction is in and out, and so that would be like -2, or actually positive 2 meters per second k hat. Okay, so you're basically writing those vectors, and you're not putting a cosine of theta or sine of theta at the end of them. If it was 4 meters per second and sine of theta, you would take whatever that sine of theta number is and multiply it by 4 meters per second, and that would be your unit vector in meters per second. Okay? So it's a way to write vectors, and it's a quick way to write vectors without dealing with sines, cosines, and all that stuff, and just get it in its base units of meters per second. Okay? And that allows us to do some arithmetic that we normally wouldn't be able to do. Okay? So if you're given a vector A that has components in the I and j directions, so in the x direction and y direction, and you're given a vector B in the x direction and y direction, then vectors A plus B is going to be vector A vector A and vector B. When you add them together, you just put the unit vectors of I together and the unit vectors of J together, and that would allow you to really quickly just add up those two units. Like this is positive 4 and positive 3. This would be a total of 7 I hat, and this would be a total of, and this was 6 and 5. This would be a total of 11, right? And then you could quickly see that. So what did I say that was? If this was 3 meters per second, and this was 5 meters per second, and they're up and up, and this is going to be, and this will be I hat, and this will be j hat, and then we write 4 meters per second I hat, and this is plus 6 meters per second j hat. Well, now that allows us to do something really quick. This will be this component right here, the x direction component of this is going to be 3 plus 4, which is going to be 7 meters per second I hat, plus 5 meters per second plus 6 meters per second, 11 meters per second j hat, which then you could really quickly go, okay, well, if you want to get the total component of that total length, you just do 7 squared plus 11 squared meters per second, and then you get the total value of that. You could do some really, it makes things really far more clear, right? Otherwise, you might have something like 2.4 cosine of 30 degrees. Well, which is more clear? Actually, it should be 2.4 60 degrees. So, which is more clear, 2.4 or 6 cosine 60 degrees or 3 meters per second, right? A lot easier to do this, okay? Similarly, it allows us to do vector subtraction really easily, right? So if you have an A vector that is, if you need to subtract the A vector from the B vector, you just subtract -3, you go 3 minus 4, so this would be 3 minus 4, which would be -1 meter per second I hat, and then 5 minus 6, which would also be -1 meters per second j hat, right? So it makes things easier to do. Also, to do multiplication, if you had to double the a hat vector, right? If you had an a hat vector and you need to double it, right? If you had to find what 2a is, right? And so let's call this again 3 meters per second I hat, and we'll call this 5 meters per second j hat, right? Well, if you had to find 2a, well, that's just going to be 2 times 3 meters per second I hat plus 2 times 5 meters per second j hat, right? So this would end up, so 2a would then just be 6 meters per second, which is pretty obvious, and then 10 meters per second, which is pretty obvious, right? So it's a real quick way to solve that vector addition stuff, okay? So it's just much more useful, much more, has better utility purposes without creating a lot of noise and distraction. So graphically, what it is this. If you have an a vector that's pointing up and to the right, then its ax component is going to be ax I, and it would be, and its vertical component would be ayj. All right. All right. Well, let's practice this again. I want you to give me the vector components. Just, we're not going to practice the unit stuff, but for right now, I just want you to give me. I want you to decompose the c vector into cx and cy. Okay? So go ahead and try this out. All right, well, I'm going to start from the origin. I'm going to make a vector up and to the right for cy, and then I'm going to add that to the cx vector, and again, it doesn't matter the order, and that'll be cx. Well, let's look at this. It looks like we start from -1, we go to 0, and then we go to +1. So it looks like it's +2 units up. So it's going to be +2 units up in the y direction. In the x direction, it's going to be to the left, okay, 1, 2, 3, 4 units to the left. So that's going to be -4 left, correct? So that means we're going to be looking for a -4 and a +2, cx and cy. So -4 and +2. So the answer is D. Well, in the next, I want you to, in this next problem, what I want you to do is take exactly what you did in this problem, but I want you to represent it as the unit vectors, okay? All right? So, again, C here is going to be Cx I hat plus Cy j hat, right? And let me write this in an area where, so I want you to write it in the form of C is going to be equal to Cx I hat plus Cy j hat, right? And that is the C vector, right? Well, we already did it, kind of, right? We found that Cx is -4 and Cy is 2. So isn't this going to be -4 is Cx, and that's going to be I hat, and Cy is going to be +2 j hat, which will be D. All right? Well, let's apply this to what we're doing in physics. Okay? So you got, here we have a problem where we have a rabbit running, well, actually, it's kind of like, looks like it's jumping up and to the left. Okay, so it's jumping at the speed of 10 meters per second in the air at an angle of 40 degrees from the horizontal. And so it's got a y direction component and an x direction component. And what they want you to do in this problem is to actually solve this in terms of its unit vectors. So they want you to represent the overall velocity of this in terms of Vx I hat and Vx j hat. Okay? So go ahead and try that out. So how are we going to do this? Well, Vx I hat is, so we need to figure out what Vx is. Okay, so it's pointing to the left, and it's by 10 meters per second, and that's at a cosine of 40 degrees. Okay, I'm just taking V and taking 10 and plugging it in here. So what does that equal to? Well, let's go ahead and we're going to go 10, and we're going to make it negative, and we're going to multiply that by 40 degrees and cosine of theta, which is 76.76. So it'll be negative 7.66. So this is going to be negative 7.66 meters per second. And that's pointing in the I hat direction. So that component is going to be negative 7.66 I hat. Okay? Oh, I forgot the units. Don't forget the units. Meters per second I hat. All right. The y direction is going to be pointed up, so that's positive 10 meters per second. Sine of 40 degrees. Okay? So let's figure out what that is. Let's put it in our calculator here. So that's going to be positive 10. Multiply that by 40 degrees. And this is going to be sine, which is 64% of 10. So that'll be what, 6.42? Actually 6.43. So this is going to be positive 6.43 meters per second I hat. Actually, that's j hat. So this then will be positive 6.43 meters per second j hat. Okay. So hopefully we've got this right. And if we look down here, yep. One thing I didn't mention, you can actually pull out the units. So maybe to simplify it a little bit more, you could say this, negative 7.66. Well, actually, they just have it written here. You could pull out the units, right? We had 7.66 meters per second in that. You can just pull out the meters per second, and then this would be the overall vector. So thing to remember, what they're saying here as a rule, is that you have to put in the signs in the forefront and figure that out, okay? So, and that's what we did when we put it in the calculator. So basically, that's how to apply unit vectors to what we're doing, okay? While we're here, sometimes you have to turn a coordinate system, and we're not going to get into this really until we get into forces, and we're going to be doing forces on an inclined plane, but I want to touch upon it right here, just briefly, okay? So sometimes if you have a vector that's pointing up and to the right, just like this, okay, there's going to be some cases, like up and to the right, just right here, where you're going to need to twist the coordinate system here. So rather than the coordinate system to be pointing positive y and positive x and negative y, rather than doing that, you're going to have to twist the coordinate system to be parallel to this line, okay? So in this case, when you twist the coordinate system here to be where the x direction is parallel to this line, you're now twisting the coordinate system, and I'm going to write this vector from the origin. The positive x is now going to be down and to the right, okay? So I'm going to write the rest of the coordinate system, okay? And when you do that, that sometimes later on you're going to make things a lot easier mathematically if you twist the coordinate system. So one of those kind of problems is when you have a force on an inclined plane, okay? And that inclined plane is tilted at an angle of 20 degrees, okay? So here's basically how to do it. And I don't want to get too far into this until we actually need to use it, and that need to use it will make this information important. But I just want to point out that it is possible to twist a coordinate system to make the math easier. And essentially these slides are how to do it, okay, and how it's applied to our system. Okay, so we're going to go ahead and stop here, and the next subject that we're going to be doing is we're going to basically take everything that we've just done and we're going to be applying it to motion. Vector addition, initial velocity vectors, final velocity vectors, acceleration vectors, and displacement vectors. And how do you use what we've just done to analyze two-dimensional motion, okay? That's going to be vectors where velocity vectors, acceleration vectors, and displacement vectors might have components in the x and y direction at the same time, okay? So we're going to be applying everything we just learned and apply it to two-dimensional motion, okay? I hope you had a good time. Bye.